Hi everybody, welcome to week 5 of Chemistry and Society. I hope your week is going well. Let's take a look and see what you've got on your plate this week. So last week you had a lot of things to do, and I know that this lab number 4 was a lot of work, but for the most part you guys tackled it and did a really good job. I probably would say that was your most difficult lab for the semester, so pat yourself on the back that you got through it, and hopefully you did well. All right, so when you're ready, you can click here to read all about week 5, your learning objectives, what you're reading, viewing, and what you're completing for assignments. But I'm just going to walk you through the modules. So chapter 4, you're reading chapter 4 and doing the Learn Smart activity online in our McGraw-Hill Connect area. Again, for those that like the PowerPoint, I especially think they're good to have on hand when you're ready to take the test. You're going to watch your third movie, An Inconvenient Truth. It's getting a little old in terms of the date on it, but the facts and the statistics unfortunately remain pretty stable compared to as to what's put in here. So there's that, and then your movie Dropbox. You guys are doing great with that. Don't forget, one half of the essay is about a summary of the movie, and one half is about how it relates to our class. And then this week's lab is the energy comparison of fuels. So we're starting our venture into fossil fuels, and then we'll also look at alternatives to fossil fuels in class. But we're going to start with just looking at some fuels and how to calculate the energy that's released with the different fuels. And so when you're ready, the Dropbox is here. I'm going to go through that lab quickly here in just a minute. But what you've got, again, the PDF of the lab, you guys are doing great with that, and then your one picture that shows your fuel setup, which is in part 2, and you in it. So take a selfie holding your sign. You guys are doing a great job with that. So let's take a look at your energy comparison of fuels. Okay, so basically what's happening here, before I even show you the information, you're going to burn 2 different fuel sources, and you're going to do it separately. One is a candle, a little tea light candle, and one is a sterno, which is a container that caterers use to heat up the bottom of those pans. So if you've ever had food from a caterer, some people use them in their own homes as well when they're having like a big party. So they're 2 different fuels inside there. They are 2 different sizes, but that's actually not going to be part of it in terms of why one might give off more heat than the other. So you're going to heat those, you're going to light those, and you're going to heat up some water. And so we're going to see which one releases more energy per gram of fuel at the end of the lab, just to give you an idea that different fuels release different amounts of energy. Okay. So you can read about combustion. That's the reaction here that happens when we burn a fuel such as a hydrocarbon. Methane gas, that would be if we were actually in the lab, in the chemistry lab, and you were using Bunsen burners. Methane is pumped into the lab. It's also what's happening if you have a gas stove at home or even a gas hot water heater. Either way, you can change your fuel here at the beginning, but requires oxygen from the air and a spark, and then it produces as products carbon dioxide and water, both of which are actually greenhouse gases. All right, so then you can read about biofuels and the different fossil fuels, things like that. Some interesting facts. I do want you to read through there. Here are some of the different fuels. Some additional ones here. Down here at the bottom, we're going to talk about the units of energy. Energy is measured in either calories or joules. In the chemistry lab, honestly, we flip between the 2 quite often. And calorie, just so you know, I'm sure you've heard the word calorie before, but be careful. There's actually 2 different units of calorie. There's lowercase c calorie, which is just what we typically use in the chemistry lab. It's the amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius. Joule is the other common unit. And then over here, this last sentence, if you read this, the term calorie with a capital C, that represents dietary, or what they call food calories. That's actually 1,000 regular, or I like to say true calories. So for instance, when you read the back of let's say a Snickers bar, and it might say it's 150 calories with a capital C, that's actually 150,000 true calories, what we're going to talk about in this particular lab. You can convert between calorie and joule, that's lowercase c calorie, true calories and joules, through this conversion here. You multiply the number of calories by 4.184. That's how many joules, 4.184 joules, are in one lowercase c calorie. Okay, so typically we use a calorimeter that would look something like this to contain the energy and it wouldn't escape to the atmosphere. We don't have anything that fancy though, so read through this. This is a really, really good experiment. If we had the money and could all have these calorimeters at home, we would do them. We can use something similar and it's going to release a little bit of energy to the atmosphere, but for the most part, for what we're going to do, it will get you through it. Again, make sure you're reading everything. I'm just kind of skimming through here to give you an overview. All the things that you need for the lab. And then again, watch the video as a reminder of how to use your digital scale. Some of you, I think last week, were including the mass of your volumetric flask for your sugar solution, your sugar water solution, and that threw off your mass and you lost a point for that. So be careful. Make sure when you have a container, you don't want the mass of the container, you want just the liquid. Or you can do a difference, a mass by difference. Get the container mass and the container plus the solution and subtract the two. Okay, so here's your big equation. Q, which is the heat energy, those calories we were just talking about, calories, equals your change in temperature, delta T, times mass, that's going to be your mass of your water that's used in the experiment, times CP, which is specific heat capacity. And since we're talking about water, different substances have different heat capacities. Here it is for water. It's 1 calorie per gram per degree Celsius. So your CP value you're going to use is 1 calorie per gram per degree Celsius. You're going to multiply that by the mass of the distilled water that you use in this experiment, and you're going to multiply that by how much the temperature changes after you heat it up with your fuel source. All right, you're going to, and this is really important here, follow these instructions. You're going to need the density of water. Okay, what should it be? Well, it should be about 1 gram per milliliter, but give or take, your water might be just a little off, and we need to account for that. So follow these instructions, put the graduated cylinder on your balance, make sure it reads 0, like I was just talking about. We don't want the mass of the cylinder, just the water, and then add 10 milliliters of water to the cylinder and record the mass. So your volume that you're going to use in your density calculation is 10 milliliters. The mass you're going to use is whatever your balance says that 10 milliliters weighs, and then you're going to calculate your density. Okay, this is the basic fuel setup. You're going to do this in an aluminum pie pan just in case some fuel or, just basically not burn your kitchen down. Definitely don't want to burn your kitchen counter. And so then what you're going to do, you're going to get your beaker. Okay, add water, about 200 mils of water in it, and then you're going to cut out some aluminum foil. You'll see what that's used for in just a second. Set this all up. Your burner will be underneath. Don't quite get it going yet. Get your little, all the stuff that you need here. The stand, the beaker, that's your setup. And then get your beaker on the stand. Get your thermometer and put that in, give that just a few minutes to sit inside your water. Your water's probably room temperature, but it may or may not be. You want to make sure you record the initial temperature of the water in your beaker before you start. Give it a couple of minutes to sit in there, and then record the temperature. And then turn on and tear your digital scale again so that it reads 0, and put your fuel canister without the lid on your scale. We want to know what the fuel source, this is the sterno, first, what that weighs before the experiment. What's going to happen if you've heard Einstein's equation, E equals mc squared, mass is going to be converted into energy when we do this experiment. So at the end, when you take the mass of the sterno at the end, it will have a lower mass. So you need to record what it is before you start burning it. You can read through all this. And then here's your piece of aluminum foil you're going to use to cover everything to try and keep the energy contained. It's not ideal, it's not imperfect or without its error, but it works pretty good. Okay, then basically you're going to light the fuel, put it under the stand as quickly as possible, put your foil, cover everything, start your timer, heat it, let it go for 5 minutes. Then take the foil off, extinguish the flame. You use this little, that's what this little cap here is for, like a little cupcake holder, but not a paper one because that would catch on fire. But you need to basically extinguish the fire or the flame from the sterno, pull it out from underneath. Insert the thermometer, record the temperature of the water, let it sit for a minute, no longer than that, and record that as your final temperature under your fuel canister. And then let your beaker cool. That takes a few minutes before you restart because you're going to do this again with a candle, okay? And then one last thing before you can set your sterno or your fuel canister aside is once it's cooled off as well, go over and take another mass of it. So make sure you tell your balance 0 and then put the sterno on that, weigh what the final mass is. Okay, then you're going to basically, as I said, repeat the whole same thing but with your tea light candle. Now here's the difference though. The tea light candle is so little and the stand is so big that you would lose a lot of the energy, the heat coming off the candle if it was too far away from the bottom of the beaker. So you create this little hammock with your with another piece of foil and get it all set up so that the tea light candle sits really close to the bottom of that stand. Again, your sterno is so big and it's so much bigger in size and height that it gets pretty close and you don't need to do this. But your tea light candle, you do. You need to create this little hammock and set it up close. And then, like you did before you do anything in terms of lighting the candle, read and record a mass of the candle before you do anything. Put your thermometer, get some water, put your thermometer in the water, record what the initial temperature of the water is, then put the whole thing back together. Cover it with foil. Let this one go for 10 minutes. Afterwards, pull out the candle, blow it off, let it cool. You're going to weigh the candle and you're going to record the new temperature of the final temperature of the water. In fact, I'd probably do those in reverse order. I'd record the temperature first, right after you blow out the candle, let the candle cool, and then go weigh it, okay? Now, as far as your pictures, I said figure 2, which was, oh, did I say figure 2? I don't remember. I want your fuel setup. So basically like this. I'd love to see it actually burning. So if you can get it to the point where you are, burning either the candle or the sterno, just take a picture at that point. Okay, the fuel setup while it's burning. I think I actually said exercise 2, and that was not step 2. But either way, that's what I want the picture of. Okay, sorry, I went too far. Okay, once you're all done, then you're going to have mass before and after of each of your fuels. So you're going to also have a mass of your water. How much water did you heat up? Because that's how much water absorbed the energy. You're going to have initial and final temperatures, and that's all that you need to do the experiment. Well, and you need your density. So the density that you did at the very beginning before we did anything with the candles, your density is in grams per milliliter. So for instance, if you use 200 milliliters of water in your experiment, you can use your density of your particular sample of water to calculate or convert from milliliters, 200 milliliters, into grams. And then that's what you use here. So again, as I showed you a few minutes ago, your energy equals change in temperature. So how much did the water heat up? Is it 5 degrees? Is it 50 degrees? Times the mass of the water that you heated, times that specific heat capacity, which for water is 1 calorie per gram per degree Celsius. And it says it again right here. Okay, and then you're going to plug it all in. This is not going to be your answer, but you can see the example here. Plug it all in and get your lowercase c or true calories. That's how much energy the water absorbed in the experiment. And then the other thing you have to do is figure out how much mass was converted into energy. And so that's grams of fuel consumed. That's the difference between the initial and final mass of the fuel. So of the canister, and then you're going to do it as well for the tea light candle. And then finally, the last thing you do is it wants to know what is the energy per gram of fuel. So you take your energy that you calculated, divide by the mass, total mass of fuel consumed, which is again the difference between before and after, and you'll have the energy per gram of fuel consumed. And they'll be different because you have two different fuels. Okay. So that's what you're going on. Then you can go on and do your questions and all that good stuff. Okay. Hopefully that helps you guys, and I will see you next week.